And in this video we'll see about magnetic hysteresis. What is magnetic hysteresis means? Suppose if you are increasing H value in a ferromagnetic substance. In ferromagnetic substance, you can assume atomic magnets are in random order or domains are in random order. Whenever you apply external magnetic field by bringing a magnet towards to it, what happens? The order of the order increases. Suppose that the field is actually like this, north, and these start aligning in this direction. So the number of magnetic poles, that is atomic magnets, align in the direction of the field start increasing when you are moving towards to that. So how field we are applying, how H we are applying in this material, and how I or B increases inside. They draw a graph here. They observe that there is a lagging of B when compared to H. So you see the phenomena of lagging of flux density. Flux density is nothing but magnetic field induction only behind the magnetizing field H in ferromagnetic substance. That what you call hysteresis. And what is a property? How it shows this property? What is a lagging means here? You see that if you bring a magnet towards to a ferromagnetic substance, the magnetic dipoles here, magnetic dipoles like this are aligned, and these are changing their direction in the direction of the magnetic field. Magnetic field is like this, so these also start align in the direction. This also turn in the other direction like this. Then the dipole or atomic magnets which are in the direction of the field start increasing. That means total field B also increases. Here H increases, B also increases, like this it increases. Suppose if you bring this magnet very close to this, what happens? Almost all of the dipoles are in the same direction, alignment takes place, and even if you increase the field H value more and more, there is no further induction inside, so it will become constant. This is a saturated point at A. So after that, even if you increase the H value, it won't increase, it becomes flat like this. Now what they are doing? They are withdrawing H value. Withdrawing H value means this magnet is moving away. Then what happen? In case of diamagnetic material or ferromagnetic material, what happen? If you remove the magnet, completely they lose their magnetic nature, and again they arrange randomly. But in case of ferromagnetic substance, what happen? Even if you remove, some are aligned in the direction of the field that remains in the same stage. That property, what do you call? Retentivity or remittance. Retentivity or remittance. What is remittance or retentivity means? Even you see that H value decreases. Up to here H value increases. After reaching saturated point, H value start decreasing. So H value decreases and it make 0. Then this graph is not following this backward. Actually it should follow the backward like this. But in case of ferromagnetic substance, it follows like this. Even H value is 0, but the field inside the ferromagnetic substance won't become 0. This OB, what we call retentivity or remittance. So once the dipoles are aligned in a particular direction, easily they won't lose their nature of alignment. Still, even external magnet is removed or external magnetic field H is removed, some B remains there. Suppose if you want to remove this magnetic field which is aligned in this, that reverse the magnet south, now bring the south pole near to this, then what happen? These are losing their magnetic nature. Initially they are in the direction of H like this. Now they try to change their direction towards to in this direction. So if you bring south means attraction, like this they are aligning now. That means what happen? If you apply a negative field here, bringing south pole means applying negative field. Negative field means what happen? This field, induced field, gradually decreases. It becomes 0 at a particular value. So how much H value you have to apply in reverse order to destroy the field which is existed here in the previous case. Here this remittance are and here retentivity is there. To remove this completely, to remove this field, how much negative field we have to apply? That only what we call coercivity. What is coercivity? Coercivity is a measure of magnetizing field intensity required to destroy the residual magnetism. Residual magnetism means that is a retentivity or remittance only. To remove that magnetic nature already aligned in the first case, to remove that, how much reverse field we have to apply, that only what you call coercivity. Suppose if you bring this magnet, this south pole very close to this, what happened? All the dipole align in the direction. Last time it is forward direction, now and backward direction they align, and field become maximum in negative side. So here also saturation point we get. More than this we won't get negative value. Suppose if you are withdrawing the magnet now, south pole is withdrawing and the pole is going away, then what happened? Some of the dipoles are disturbed, but remaining dipoles are same direction as initial, that is in the same direction like this. That means even negative H is 0, but some field is there in the ferromagnetic substance. To make it to 0, again you have to apply a positive H value, so you should increase the H value. So this how a ferromagnetic substance, on applying magnetic field and removing magnetic field, that we can say a cycle of magnetization. And what happen, it follows different paths. So it shows first initially if there is no external field, and it follows like this, then it follows this curve, and now it follows a different curve. So it has a memory of a previous situation, and this kind of nature what we call hysteresis curve. Hysteresis curve, a person having a mental disorder behaves like different persons, they call hysteresis patient. Like that here also we can call this nature what we call hysteresis curve. So initial field is not there, it starts with 0, but even field is 0 here in this case. In these two cases also field is 0, but field induced inside is not 0. It has some different value here. That what we call hysteresis nature. So using this hysteresis curve, we can check the property of magnetic property of the ferromagnetic substance. Suppose if this area, that is area of this loop, that is hysteresis loop, HB loop is more, we can say energy loss is more. Suppose if you are magnetizing one material and demagnetized, in that process, in a cycle of magnetization, it loses more energy. So more area inside the loop is more, and energy loss also more. So you see, energy area more means you can say retentivity more and coercivity also more. What is retentivity? And even after external field is removed, how much magnetic field remains there inside the material, that is what we call retentivity. What is coercivity? To remove that magnetic field, and how much reverse field we have to apply, that what we call coercivity. OC is coercivity and OB is retentivity here. If this area is more, energy loss is more, that material and get heated during a process of increasing and decreasing field, that metal get heated. This type of metals are not suitable in case of magnets we are using in the transformers, AC motors, AC generators. We are using some type of magnets. For that magnets, these are not suitable. What is the reason means? In case of AC generators, motors, magnetic field continuously rapidly changes, increases and decreases. So that means what happens, this magnetic cycle takes place, that is hysteresis loops takes place. If this area is more, and that will be energy will be converted to heat energy, and there is a chance to damage the instrument because of increasing heat energy in case of transformer or AC and DC motors. Suppose if you take soft iron or silicon iron they call it a soft iron or silicon iron they call sterling metal, and those type of metals have this area very less, means they have very low retentivity is from O to C here, and very low coercivity. So these metals are used, less area means energy loss is less, and these metals are used for temporary magnets. And temporary magnets means where we are using, that already we discussed, that is in case of transformers. And if you send AC current through the transformer, magnetic field rapidly increases and decreases takes place. Suppose if you are using a steel has a highest area in the hysteresis loop. If you are using this, means what happen? Easily it get heated, and easily temperature of the instrument increases, it get damaged. That's why they use soft iron core inside a transformer or AC and DC generator, AC generator and AC motors. Soft iron, because area is less, retentivity is less, and coercivity also less. But to make permanent magnets, we should use a steel. So that means once you magnetize, and even if you remove the external field, the total magnetic field, most of the magnetic field remains there inside for a long time. So even if you apply external field for a huge external backward field, reverse field, then only it loses its magnetic nature. Otherwise it won't lose easily. Because of that, what happened? These type of metal, they use for permanent magnets. For long time, the magnetic nature remains there. For that, OB, resistivity, remittance is more, and coercivity also more. Area is more. And area less for temporary magnets and repeated change in magnetic field cases, we can use this. Permanent magnet or fixed magnetic field means you need to use this type of metal, that is steel. Now, which type of materials are used for permanent magnets? Which type of materials are used for temporary magnets? That we'll see. So here you see an important point. So what is permanent magnet? For long time, and the magnetic nature should be there with the material. It has large retentivity, large coercivity, and large permeability. High permeability should be there for permanent magnets. And best suitable materials for this cobalt, steel, and like materials is there. Steel is preferred for making permanent magnets because its coercivity, and already we discussed that large retentivity, large coercivity, and permeability. Where they use this type of magnets? Galvanometers, voltmeters, ammeters. In galvanometer, voltmeter, ammeter, we need a horseshoe magnet which is having high magnetic field in a small region. That's why they use this permanent magnets in galvanometer, voltmeter, ammeter, microphones, loudspeaker, telephones. And next, temporary magnets. Temporary magnets means, and these materials should have nature easily gaining magnetic nature, easily lose their magnetic nature without heating the substance, heating the instrument. Means hysteresis loop area should be very, very less. Those type of materials are used for this. And what are the suitable materials? So this is where electromagnet, where they are using electromagnets, cores of transformer and motors and generators. We already discussed that. Which type of metals are suitable for this? Soft iron, Mu metal. It is a combination of nickel and steel, combination of nickel and steel. That what you call Mu metal. Sterling metal means you see that is silicon iron only. They call sterling metal here. Is a best example for ferromagnetic materials which are used for temporary magnets. And where they use electrical bells, already we discussed in making of electromagnetic and cores of transformer, and additionally electric bells, loudspeakers, telephone diaphragms. They use this type of temporary magnets here. And temporary magnets, what is the nature? They have low coercivity and a small hysteresis loss and low retentivity. There, high retentivity, high coercivity. And here, low retentivity, low coercivity, and a small hysteresis loss required for temporary magnets.